Have you ever actually stopped to think about what's happening inside your computer when you hit the plus sign? It totally feels like magic, right? But it's not. It's really this precise, microscopic dance of electricity and logic. Today, we're going to pull back that curtain.
All right, so let's just dive right in with a super simple question. We all know 5 plus 9 is 14. But how? How does a machine that's literally made of silicon and metal get to that answer? I mean, it can't know math like we do. It's basically just a rock that we zapped with electricity and tricked into thinking. So it has to follow a very, very literal set of instructions. To find out how, we're going to crack open the brain of a real classic, the Intel 8085 microprocessor. This thing is from the 1970s. But here's the thing. The basic principles we're going to see right here are still the fundamental building blocks for even the most powerful chips in your phone or laptop today. Okay, so before we can follow the recipe for addition, we got to get familiar with the chef's tools. We need to understand the basic little components inside this microprocessor that it uses to get all its work done. First up, you've got the microprocessor itself. Let's think of it as the head chef. Now, its job isn't to cook, but to read the recipe. And that recipe? That's our program. The chef just follows the instructions, one by one, perfectly, millions of times a second. It's wild. Now, every good chef needs a place to hold their prepped ingredients, right? Little bowls and stuff. Well, that's what registers are. They're like these tiny little scratch pads or post-it notes right on the processor. They hold numbers so the chip can grab them instantly. They're not for long-term storage, just for the task at hand. And in our case, we're going to be using registers named B, C, and H. And then we have the star of the show, the accumulator. It's also known as register A. Look, if the other registers are just scratch pads, the accumulator is the main workbench. It is the only place the actual math happens. Ingredients get brought here, the work gets done, and the final result is stored right back on that same workbench. All right, we know the tools, so let's see them in action. We'll start with the most basic recipe our little chef can follow. Just adding two numbers where the result is simple, with no need to, carry the one. So here it is, the recipe, or what programmers call an algorithm. And you'll notice right away, it's not just one step. First, the processor moves one number to a temporary spot, register C. Then, it moves that number over to the main workbench, the accumulator A. Only then does it bring in the second number, do the actual addition in step 5, and then it leaves the final answer sitting right there on the workbench. Let's just zoom in on that crucial step for a second, the addition itself. In programming terms, the instruction is just add H. That's it. This just tells the chef to take that 8-bit number, which is just a way of writing a value in binary, from the H scratchpad and add it to whatever's on the main workbench. Simple as that. And this is a great illustration of how programmers actually visualize that step. In a flowchart, that entire action gets boiled down into a single, simple block. It's just a really clean, logical way to map out the whole process before you write a single line of code. But here's where it gets really interesting. This is how the machine sees this. See, that add the H command is just a human-friendly shortcut called a mnemonic. The processor itself only understands the instruction's location in memory, its address, and the raw code. So this table is basically the translation from our human idea to the machine's cold, hard reality. Okay, that was easy enough. But what happens when you add, say, 9 and 5? The result, 14, involves carrying the 1. A simple chip doesn't have fingers to count on, so how does it handle that extra bit of complexity? So check this out. On the left is our simple recipe. It's just a straight line. But on the right, for handling a carry, notice the new steps. The absolute key here is this decision point. Jump on if no carry. The processor now has to check a special carry flag, a tiny, single bit of memory that flips from 0 to 1 if the sum is too big, and then decide whether or not to take an extra step. This right here, this is the heart of the new logic. The program checks that carry flag. If the flag is 0, meaning no carry, it gets a command to literally jump ahead and skip the next instruction. If the flag is 1, it just ignores the jump and continues to the next line to handle the carry. This simple, if this, then that logic is the absolute foundation of all modern computing. It's that important. And here's what that decision looks like in the machine's language. JNC, or jump if no carry. This is a huge moment. The ability for a program to make a choice based on a condition, to follow one path or another, is what elevates a simple adding machine into a true computer. All right, now that we've pretty much mastered addition, let's flip the script and look at subtraction. You might think it's a whole new world, but you'll probably be surprised at how similar the underlying logic actually is.
Just take a look at this recipe. Does it feel familiar? It should. We move the first number to the workbench, move the second number to a temporary register, perform the operation, and store the result. The structure is almost identical to our simple addition.
And here's the only real change in the recipe. Instead of ADD, the key instruction is sub. It just tells the processor to take that 8-bit number in register B and subtract it from the value that's sitting on the main workbench, the accumulator. And in the machine's language, it's just as elegant. A single direct command, sub B. The beauty of how these microprocessors are designed is that complex concepts get boiled down into these incredibly simple, fast, and efficient instructions. So we've been looking at these individual calculations under a microscope. Now, let's zoom all the way out and connect these tiny, tiny steps to the massive computational power we all have today.
So what's the big takeaway here? It's that at its core, a computer isn't smart. It's just an incredibly fast and obedient chef. It follows very simple recipes using its scratch pads and its workbench. Every single thing your computer does, from playing a video to sending an email, is built from billions of these primitive little steps, moving data, adding, subtracting, and making simple jumps. The magic isn't in how complex the steps are, but in the blinding speed of their execution. You know, the simple steps we saw on that old 885 processor took a few microseconds. The chip in your phone has billions of transistors, performing billions of these same kinds of operations every single second. So the next time you tap your screen, just remember the invisible, lightning-fast dance of logic happening right beneath the glass. It's not magic. It's just a really, really good chef.